Moving on to a pure inductor circuit, a pure L circuit, where we introduce an inductor to replace this empty space here. We put in an inductor. So what will happen is, if we design a circuit in a way that the current is varying with I naught sine omega t, if the current is varying this way, we will measure the potential difference across the inductor to be varying with V naught sine omega t plus pi over 2. So we see that the phase of the current and the phase of the voltage is different. So we can deduce that there's a phase difference between the sinusoidally varying current and the sinusoidally varying voltage. So you see that the plus pi over 2 is here with the voltage, whereas the current is just omega t. So we can make a conclusion that the voltage is actually leading. You see the plus here? The voltage is leading the current by pi over 2. So you see that V is actually leading I by pi over 2. And because we know that V is leading I, we can find the phase angle to be just equals to positive pi over 2, or you can call it positive 90 degree. Both are fine. If V is leading I, then the phase angle should be positive. If V is lagging I, the phase should be negative. So this is how we generally do it. You'll see the idea clearer later when we move on to phasor diagram. Okay, so in the lecture, we continue to derive through the equations, and we find out that V naught is actually equals to I naught omega L. So we build this equation, V naught equals to I naught omega L, which we know if you transform it to root mean square, it will be root mean square equals to, it will be V root mean square equals to I root mean square omega L. So these two are transformable between each other. So again, once you reach this stage, we have to remember we want to find the ratio of V naught to I naught, or we want to find V naught divided by I naught. So if you take V naught divided by I naught, just by shifting the I naught over down there, you'll find that it will be equals to omega L. So this omega L deserves a name because it carries the ratio between V naught and I naught. So you give it a name, reactance, but since it's a pure L circuit, it will be called an inductive reactance. So we know from this derivation here that the inductive reactance, which we call an X subscript L, is equals to omega L, which is also equals to 2 pi FL. Okay, so if you notice, if you compare it, the inductive reactance with the capacitive reactance, you see that the inductive reactance here, the frequency is directly proportional to the reactance. Whereas for capacitive reactance, you see that the frequency is inversely proportional to the capacitive reactance. So you expect this capacitor and this inductor will behave in the opposite way. So what do I mean by opposite? If you remember from pure capacitor circuit, higher frequency means by lower reactance means more current can pass through. Higher frequency generates greater current. Lower frequency generates lower current. So this, we call it as high pass filter. But if you move on to pure inductor circuit, you see that high frequency will actually cause the reactance to be larger. So if our reactance is larger, it will actually bring down the current that is flowing through the circuit. So high reactance due to high frequency can bring down the amount of current flowing through the circuit. So in that case, we can see that high frequency will generate low current, whereas low frequency will generate high current. Low frequency generate high amount of current. So when you have low frequency to generate greater amount of current, we can say that the low frequency information pass through, because the low frequency actually generate greater effect. It generate greater current. So the low frequency information generate greater current. So we call this information manage to pass through. So we call this kind of filter low pass filter, because low frequency information generate greater current, whereas higher frequency generate low current. So you can think of it as the information not getting through. Okay, the information does not bring out a very big effect. It does not bring out a great amount of current. So you can see that high frequency information is being blocked. So high frequency get filters out, low frequency get to pass through. So we call this kind of circuit, a pure L circuit, a low pass filter. So low pass filter, let's say you are having a speaker, right? A speaker usually have a specific, let's say you are, you have a very expensive speaker with a speaker specifically producing bass sound, another speaker hole purposely producing a higher frequency sound, the treble. Okay, so if the bass, for the bass speaker, the speaker producing bass sound, you need to remove the high frequency. So to remove the high frequency, you need to use this low pass filter. So what kind of current is produced is only for lower frequency portion of the sound. So the bass are able to generate current to cause the membrane to vibrate. The higher frequency sound will not cause the vibration of the membrane because it will not generate great current. So that's the bass speaker. Okay, if you are moving on to another speaker that produce higher frequency sound, then the high frequency sound will probably install a pure C circuit, because a pure C circuit has a you want higher frequency sound to be amplified. So the higher frequency sound will cause a greater amount of current. So the higher frequency sound causes the speaker membrane to vibrate. Whereas lower frequency sound in the bass section will not cause a great current in a pure C circuit. So essentially we can say that the bass sound is actually getting filtered out in this speaker if you use a pure C circuit. So this is the purpose of having a pure C and pure L circuit is to function as high pass filter and low pass filter. Okay, so for pure L circuit, low frequency causes low inductive reactance. Low inductive reactance causes greater amount of current. So you want low frequency, it can pass through. High frequency will not generate much current, so cannot pass through. Getting blocked, getting filtered out. So this is pure L circuit. Let's proceed to solve questions regarding pure L circuit. Calculate the potential difference across an inductor of inductance 5 Henry when an alternating current of 20 milliampere and frequency 50 Hz passes through it. So we have an inductor. Then this inductor here has an inductance of 5 Henry. Then you are supplying it with an alternating current. Okay, it's not supposed to draw like this, but never mind, you get the idea. So the alternating current is 20 milliampere. They didn't mention its peak, so it should be the RMS value. So its RMS equals to 20 milliampere. Then the frequency is equals to 50 Hertz. So now they ask you to find the potential difference. Again, they didn't specify the potential difference, whether it's peak or RMS, so we assume they're asking for VRMS. If they didn't tell anything, we are assuming it to be root mean square. So let's find the potential difference. How are we supposed to find the potential difference? You know you need this kind of equation that relates between VRMS and IRMS. So what should you complete this equation with? It should be an inductive reactance, because this is a pure L circuit. There's only inductor connected to this circuit. So it's a pure L circuit, so it will be VRMS equals to IRMS XL. So we know the VRMS value, but we don't know the XL. But we can still break down this inductive reactance here to its smaller parts, which is just omega L. And of course, you can break it further down to be IRMS 2 pi FL. Okay, so I think we have broken it down enough. We have IRMS, we have frequency, we have inductance. So now it's a matter of substitution. So it's 20 times 10 to the power of negative 3. There will be 2 pi. The frequency is 50 Hertz. The inductance is 5.0. So from here, if we do a bit of calculation, we'll figure out that the VRMS should be equals to 10 pi volt. So this is the VRMS value. If you're not comfortable of leaving it as 10 pi, you can also break it down into digits, decimals. So it will be 31.4 volt. Okay, so that's the root mean square value for our voltage. Okay, so that's all for example 7.